Hello again, and one real quick note I wanted to make. Yesterday when I was completing the last problem, I noticed that I forgot a part of it. So express the candle's height as a function in terms of time. And I had written an equation here, but forgot to fill it in there. So instead of x and y, we should be using t for our input, and instead of y, it's going to be h of t. So it's going to be basically the same equation, negative 1.75, but instead of x, it's going to be t for our input, and then plus 20. All right, so that actually is a linear equation, which is the next concept, but we are going to be, besides linear equations, we'll be looking at inequalities and functions. So this ties right into what we were doing. All right, so again, these problems were from the Indiana Department of Education website, along with the standards that are the critical standards. So determine whether each relation represents a function, y or y not. So when you're determining whether something is a function or not, you're looking at basically the x values or the domain. And if you're given, it depends on what you're given. If you're given a list of ordered pairs, it's just the x values that you need to look at. So if the x values are all different, then you do have a function. It's basically each input has to have exactly one output, is so to speak, is another way of putting it. So it cannot have more than one. So a good analogy that I had given my students, I give my students, is that if I have a bowl of candy and everybody is allowed to take exactly one piece of candy, there might be some people that choose the same type of candy, but as long as each student only chooses one type of candy or one piece of candy, it is still representing a function. But if you have some students that pick more than one piece of candy, now it's something that's not a function. So each input has to have exactly one output, but the outputs could be the same. So if any of these y values or your outputs were the same, that's okay. Just like the kids can have the same type of candy. They just cannot have more than one. So each x value can have only one y value or output value that goes with it. All right, so again, this a here, it is a function because each x value has exactly one y value. I guess I don't need a comma there, but so it is a function because each x value has exactly one y value. Good. So in the next problem it says consider a relation such that the independent variable represents the people in a classroom. So our independent variable is usually our x value. So that represents the people in the classroom. And the dependent variable, which is usually your y coordinates, represents the month in which they were born. So does this relation represent a function? So this goes along hand in hand with what I was using the analogy with the students and everybody getting one piece of candy. But some of the people might choose the same type. Well, if you think about this, the people in the classroom, you can only have, each person in the classroom can only be born in 1 month. They cannot be born in 2 separate months. So, but some people may be born in the same month, and that's okay, as long as each input variable or independent variable, or the input, like the x or person in the classroom, has exactly one output value or month that they were born, which is true. So yes, this represents a function because each person can only have one birth month, or 1 month in which they were born. So yes, this is represents a function because each person can have only one birth month or 1 month in which they were born. Okay, so now vice versa. Let's say we flip it around and we say now that the independent variable is the months of the year, and the dependent variable represents the people associated with the month. So now, for example, if we have January or February and March and so on, all right, so these are basically our input values. If these are our independent variables, and then our output values, well, you might have John that was born in January, but you also might have Sarah that was born in January. So that input value of, or independent variable, the month, can have more than one person that was born in January. So that would not be representing a function, because these input values, the independent variable, has to have exactly one output, but it would be possible to have two if we're talking about the people in the classroom, and if January, there's going to usually be more than one person that's born in one of these months. Maybe January only has one, but February might have two, and March might have three. So this would not be a function. Again, because 1 month can have more than one person born in that month. So there may be more than one person born in that month. Might have been a better way of saying it, but oh well. So hopefully you made sense of that. Moving on now to the next problem. And in this problem, I think this carries on with the next example. So they're asking if this table, I believe, is a function. Yeah, so it has the same directions as the last problem. So they're asking, is this table representing a function? So if you look at, again, just the input values or the x values, there are two x values that are the same, but they have different output values. So this would not be a function. So it's not a function because the x value of -6 has more than one y value. So that one is not a function. Okay, moving on now. Graphing is an extremely important part of mathematics, especially at the high school level and beyond. So in this problem, we are graphing. I've got 4 different equations that we're going to graph, and we are going to graph and label each equation on, I guess I have 2 coordinate grids to use here. So I will graph H and G, the first 2 on this graph, and then, I'm sorry, F and G on the first graph, and H and K on the second graph. So when you're graphing linear equations, you can make a table of values and substitute numbers like -2, -1, 0, 1, and 2. However, the easiest way, the way that you should be able to do it at this point in high school, is to start with the y-intercept. Hopefully you know that the y-intercept is the constant, and that is because if you were to substitute 0 for x, it would equal -3. So 0 times 3 is 0, minus 3 would be -3. So that is your y-intercept. So 0, -3 would be my starting point. And then from that point, my slope for this first problem is a +3. When a slope is positive, it's going to be going up to the right, but also could be going down to the left, depending on how you look at it. But from left to right, it should be increasing. If it's not a fraction, you can make it a fraction to think about rise over run. So we're going to be going up 3 units, and then to the right 1 unit, but we're starting at the y-intercept. So from that point, we'll go up 1, 2, 3, and to the right 1, and put another point. Up 1, 2, 3, and to the right 1, put another point. You really only need to graph 2 points to draw a line. However, since I'm doing this by hand, and I want it to be as precise and accurate as possible, I'm going to do more than one. But if this is a computer doing this, you would only graph 2 good points and then let the computer draw the line. All right, so that one I'm going to label it is F. The next one is going to be G. Oh, one other thing I wanted to mention. So if you were to substitute 1 into the equation for x, 1 times 3 would be 3, minus 3 would be 0. So the point 1, 0 is on the graph. So again, if you were to make a table or plug in some of these x values, again, if I plugged in 2 for x, 2 times 3 would be 6, minus 3 is 2, or minus 3 is 3. So 2, 6, or oh my gosh, 2, 3 is on your graph also. So again, you can plug and chug to get some points or use your y-intercept and your slope. All right, so for the next one, g of x, my y-intercept is the point 0, 1, which is right there. Remember, it's on the y-axis, not the x-axis. But my slope is -2. So do you see how I made it a fraction? That's to think so that I can think about the rise over the run. However, since it's negative, it's going to be going down from left to right or decreasing from left to right. So from my y-intercept, I'm going to go down 2 and then to the right 1. Down 2 to the right 1, down 2 to the right 1. If I needed to, I could extend the line in the opposite direction by doing the exact opposite. Instead of going down and right, I would go from this point up 2 and to the left 1. So all of those points are on this line. Again, if you were to substitute these x values into the equation, so if I were to substitute -1 for x, I would get 2 plus 1, which is 3. If I substitute 0 for x, I would get 0 plus 1, which is 1. If I plug 1 in for x, times -2 would be -2 plus 1 would be -1. So you can see all those points would indeed be solutions to your function. And then we're going to label that g. All right, so the next one now is h of x. So if you notice, h of x does not have a constant being added at the end. In that case, you could put a plus 0 there, but that is going to be your y-intercept. So the y-intercept for this equation is going to be 0. Again, if you were to substitute 0 for x and multiply by 2/3, you get 0. So that would be your output. So your input would be x, but your output or 0. Your input would be 0, and your output would be 0. So that is your y-intercept. Now I'm going to graph this one on my second graph so it's not looking too cluttered. So 0, 0 is the y-intercept, my starting point. But my slope this time, it's again positive, but it's 2 over 3. So since it's positive, it's going to go up to the right or increase to the right. So we're going to go up 2 spaces and to the right 3 spaces. Or you can plug and chug and make a table of values. So going over here, starting at 0, 0, I'm going to go up 2 and to the right 1, 2, 3. If I went up 2 and to the right 3, I'd be off the graph. But if I wanted to, I could extend the line in the opposite direction, go down 2 and to the left 3. But these should all line up and be in a nice straight line. Again, on the computer, you only need to have 2 accurate points to draw your line. And then I'm going to label that H. All right, one more. So the last one, the equation is k of x equals -4/3 x plus 2. So my y-intercept is a different color. My y-intercept for this one is going to be 0, 2. Again, it's on the y-axis, not the x-axis. So we're going to graph that point right there. But my slope is negative this time, which means I'm going to go down right, down 4 to the right 3. So going back to my graph, starting at +2, I'm going to go down 1, 2, 3, 4 to the right, 1, 2, 3. And if I can't really graph more than those 2 points, so to make it a little bit more accurate, I'm going to get my ruler out to make a nice straight line. And if I was doing this on the computer, like on the ISTEP, you would get it that the computer would create a nice straight line for you. All right. So there you have it. There's 4 different equations and 4 different lines. The next question, part B, it says to create a table of values for each equation, then graph each equation on the same coordinate plane. So we're going to graph all 3 of them here and describe the similarities and differences among the graphs of the equations. Oh, one more thing that I wanted to mention. You don't have to start with, if you're given an equation in slope-intercept form, that is the best way to graph a line, but you don't have to be given an equation that's in slope-intercept form in order to graph it. You could start with any point. If you're given any point that's on the line, you don't have to start with the y-intercept. You could start with any point that's on the line if you know that that point is a solution of the equation or the function, and you know what the slope is. So hopefully there's an example of that later on. All right, so going back to this one, we're going to complete this table of values, and you notice that all the x values are the same, but the functions or the equations are different. Here we're taking 2 times x, here we're taking x to the 2nd power, here we're taking 2 to the x power. So they're all a little bit different, and then we're going to talk about what type of equation each one is. So if you multiply all of the x values here by 2, -2 times 2 is -4, -1 times 2 is -2, 0 times 2 is 0, 1 times 2 is 2, 2 times 2 is 4. If you square all of these values, that's basically multiplying it by itself. So a -2 times another -2 would equal a +4. -1 times another -1 would equal a +1. 0 squared would be 0, 1 squared is 1, 2 squared 4. So they all end up being positive. When you square a value, a number, whether you have a negative number or a positive number, if it's being squared, you get a positive outcome. And then the last one, oh, I wanted to use a different color. Let's go back and put these in purple. And then the last one is 2 to the x power. So this one is an exponential function. When you take something to a negative exponent, so we're plugging the -2 into the exponent. So I'm going to do that one off to the side over here. So -2 to the -2 power. Hopefully you can see that okay. When you have a negative exponent, it does not mean a negative number. It means the inverse or the reciprocal, or make it a fraction by putting it over 1 is what we need to do here. So we're going to make this negative exponent positive by rewriting this as 1 over 2 squared. So 2 to the -2 power, rewritten, is 1 over 2 squared. Notice the negative becomes positive, but neither one of these numbers are negative. And then 2 squared is 4, so our y value is actually going to be 1/4. If we substitute -1, so if we take 2 to the -1st power, basically we are taking the reciprocal or the inverse of the 2. So again, we would put 1 over 2 to the 1st power. That negative becomes positive, but anything to the 1st power is itself, so 1 over 2 to the 1st power is 1/2. All right, the next one, we have 2 to the 0 power. Well, anything to the 0 power equals 1, and that's something that is a rule that you need to know. And then if you take 2 to the 1st power, it equals itself, and then 2 to the 2nd power is 4. So we've got 3 different types, 3 different tables here. So notice each of these outputs are different. Now, I mentioned that this was an exponential equation. We call it an exponential equation because the variable is in the exponent. And when you graph it, if we graph -2 and then +1/4 would be about right there. -1, 1/2, 0, 1, 1, 2, and 2, 4. When you graph those points, it creates a smooth curve, and this particular equation is exponential growth because it's increasing from left to right. Another thing you'll notice about exponential equations is that they have a what's called an asymptote, where it's a line that basically that cannot cross. In this case, this cannot cross the x-axis. So the x-axis, which is y equals 0, would be the asymptote. A-S-Y-M-P-T-O-T-E. I know that's kind of a funny word, but it's y equals 0 or the x-axis. So exponential equations will have a line that it cannot cross. So if you were talking about, asked what the domain or range was for this thing, the domain, since it does keep going left and right forever and ever, would be all real numbers. However, the range, your y values, since it cannot equal 0, so there's no way that you can take 2 to a power and for it to equal 0. But it's going to keep going up forever and ever. It's also never going to be negative since it can't cross that x-axis. So your domain for exponentials would be all real numbers, or you can use a symbol for all real numbers, but your range would be all y's that are greater than 0, and it's strictly greater than 0, not even equal to 0. So that's your exponential function. The middle one is what we call a quadratic function because the x is squared. It's to the second power. So let's put that in there. Quadratic. And it's because of the x squared that makes it quadratic. We'll talk about its domain and range in a minute. So I'm kind of expanding on what this problem is asking us to do, but that's okay. -2, 4 is right here. -1, 1, 0, 0, 1, 1, and 2, 4 are your points. So this again is going to create it's going to be a smooth curve, and both ends of the graph are going up. So it does decrease from left to right and then increase. So as far as domain and range, it does continue to go left and right forever and ever. You can plug in any negative number, positive number, or 0 for x, so that your input value can be any number, so all real numbers. As far as the range goes, your lowest y value, if you look at the y values, you can have a y value of 0, but all the other y values are going to be going up, so, or above 0. So your range for this one would be y is greater than or equal to 0, where the last one was just y greater than 0. So they're a little bit different, kind of similar, but a little bit different. Okay, and then your linear equation will be a nice straight line. So let's graph the points first. -2, -4, -1, -2, 0, 0, 1, 2, and 2, 4. So this is what we call a linear equation, and it's because your x is to the first power and it's not in the denominator. That would be a different type of function. As far as your domain and range, since you can basically plug in any number for x, you can plug in negative numbers, you can plug in positive numbers, you can plug in 0. So again, the domain for a lot of these are all real numbers. But in this case, your range will also be all real numbers, because if you look at the line, it's going to keep going down forever and ever and up forever and ever. Your y's can be negative, positive, and 0. So both domain and range for your line will be all real numbers. And the only thing that would change that is if it was a story problem or if there were limits to what you were able to put in for x. Okay, so hopefully I have verbally described some similarities and differences amongst the graphs, but hopefully I've given you enough information where you could write out some similarities. You could also see that they all have the 0.24 in common. The exponential and the linear graph are both increasing from left to right, but the quadratic has a turn in it. It decreases and then increases, so it's going to do both. So there's different things that you could discuss about similarities and differences. All right, moving on to the next one. So in the next problem, we have a word problem, which everybody loves. Samantha starts with $20 on a gift card to make an ice cream shop. She plans to spend $3.50 on each $3.50 of the gift card each week. Okay, so we haven't really gotten into what we want to do with it yet, so let's just keep reading. Joe also has a gift card to an ice cream shop. So we don't know what the value is, but Joe has a gift card to an ice cream shop and plans to spend his money in a similar way, so probably a little bit each week. The amount he has remaining on the gift card, Y, so Y is representing the amount he has remaining on the gift card. So that's important that you understand what the variables are. And after X weeks, so X is the number of weeks, can be found in this equation. So looking at the equation, can you see from the equation what these numbers are representing? Well, if Y is the amount of money he has remaining on the gift card, and X is the number of weeks, it looks like he's starting with 50 and subtracting 7 each week, because X is the number of weeks. So that's so basically we could write here, I don't know if that we have to write this, but Joe has a $50 gift card and will be spending $7 each week. Okay. All right, so now continuing, it's so hopefully that made sense that this equation represents the amount of money that he has left. He's starting with $50 and it's decreasing $7 each week. So now the question is, assuming that Joe and Samantha spend their gift cards as described, who spends at the fastest rate or faster rate? So who spends at a faster rate? So the rate is basically our slope. So Joe looks like he's spending, so the slope is always with your variable or your input variable. So the -7 is our slope in this case, or your rate. So he's spending $7 per week, and looking at Samantha's information, she's only spending $3.50 each week. So Joe, and then it's asking us to explain the answer. So Joe is spending $7 per week, which is more than Samantha, or which is a faster rate, since they're saying who spends at a faster rate, so we probably should use that terminology, which is a faster rate than Samantha, who spends $3.50 per week. All right, so that answers that question, and we've explained ourselves. So then it asks us who starts with more money in their gift card, and again, explain your answer. So in the information, it's telling us that Samantha had a gift card for $20, but in this equation, you could tell that Joe has a gift card for $50. So that's his Y. If you look at the equation, it's basically your Y-intercept. So the Y-intercept is your constant. If we were to write an equation for Samantha, the equation would be Y equals 20, which is your starting value, minus 350x, or minus 350 per week. So again, you could rewrite it. You could put the negative 350x first and then plus 20 so that it's in slope-intercept form. But either way, it still represents the same thing. So 20 is your constant either way, and 50 is your constant here. So those are your starting values. And the amount of money that's on the card is decreasing, so your slope is going to be a negative rate. But here in Samantha's equation, it's negative 350. In Joe's, it's -7. So who starts with more money on their gift card? And explain. Joe starts with $50 which is more than Samantha's $20 gift card. So there we have it. Joe starts with $50, which is more than Samantha's $20 gift card. So hopefully that answers it and explains it adequately. All right, so moving on. Still working with linear equations and inequalities is this lesson. 2 daycare programs have open enrollment throughout the year. Daycare A has 7 children enroll. So this is daycare A. 7 children enroll per week and has 30 children enrolled after 4 weeks. So that's information about daycare A. And then in daycare B, for daycare B, we have a table here. The number of children, so the table B below represents daycare B. The number of children as a function of time in weeks is given by the following table of values. So here's the number of weeks, and here are the number of children that are enrolled each week. And then they want to know which daycare accepts more children each week, which daycare has had more children when it first opened, and then the graphs below show the distance. Oh, that's another problem, sorry. Okay, one other thing you may have to do with information like this is actually write an equation to represent the number of children that would be enrolled per week. So let's look at daycare A. So if daycare A has 7 children enrolling per week, that sure sounds like a rate. And usually your rate is your slope. So your slope, or rate of change in this case, is 7. Now, this 30 children enrolled after 4 weeks is just one data point, kind of like one data point here when they're saying after 2 weeks, 23 children were enrolled. After 4 weeks, 41 children were enrolled. The 30 children enrolled after 4 weeks is one data point. So you have a slope and you have basically a point, which was, now be careful that you put the numbers in the right spot if you had to write the equation. 4 is your input value, or your weeks, and 30 is your output value, or your children enrolled. So 4, 30 would be your x and y value. So once we've got a slope and a point, we can then write an equation to represent daycare A by using point-slope form, which is y minus y1 equals m parentheses x minus x1. So the 4 is going to be our x1, the 30 will be our y1. And we're going to put 7 in for our m. Jumping ahead of myself, so y is part of the equation, minus y1, which is 30, equals my slope, which is the 7 children being enrolled per week, and then x minus my x1, which is 4. But I don't like to, I don't want to leave this in point-slope form. I want to get it into slope-intercept form. So I'm going to distribute so that I have y minus 30 equals 7x minus 28, and then add 30. So then y equals 7x plus 2. So what does this tell us? Well, still our rate of change is 7 children per week, but the 2 now is our starting value. So this is what we started with. 2 children, maybe in the daycare. That's basically our y-intercept. So at week 0 we had 2 children already, but then they're increasing 7 children per week. All right, so that's the equation for daycare A. Now let's look at daycare B. So instead of giving us a rate and a data point, they're giving us 3 data points. Well, you only need 2 data points in order to write an equation of a line. So I'm just going to use the first 2 since the numbers are a little bit smaller. So I'm going to call this x1 and y1. call this x2 and y2. And then my slope formula is y2, which is 41, minus y1, which is 23, over x2, which is 4, minus x1, which is 2. So then when I subtract the 41 minus 23, I'm going to get, what, 18 over 2, which equals 9. So the slope for this one is 9, which basically, if we were to interpret that slope, means that the daycare B is increasing by 9 children per week. So that gives us enough information now to answer the first question. Which daycare accepted more children each week? That would be daycare B, because they're accepting 9 per week, where daycare, so that's B, right? Daycare B, where daycare A was only accepting 7 per week. So, so daycare B accepts 9 per week. Okay, so then which daycare had more children when it first opened? So now this question here is basically asking, can you interpret the slope? And but the second one, when it first opened, this question is asking basically, can you interpret the y-intercept, or your starting value? So the y-intercept for this for daycare A was 2, or so that was what they started with. So we do need to find the y-intercept for our our daycare B. So to do that, you can use point slope form again, and you can plug in the slope and then one of the data points and then put it into slope-intercept form. Or we could use y equals mx plus b. So I'm just going to show you a different way of finding the y-intercept. And I've got to find some space here. Let's see. I'm going to go to the top of the page. Nah, I'm just going to try to squeeze it in here. All right, so if you know your slope-intercept form, y equals mx plus b, to find the y-intercept, you could temporarily substitute one of its points for y and x, and then use the slope that you found, 9, for m. So this is just an alternative to using point slope form, but point slope form would work just as fine, just as well. All right, so if I'm going to take this y value, 23, and temporarily substitute it in for y, and then I'm going to use my slope, which is 9, substitute that, and then substitute the x value that was with that 23, which is 2. And now I have an equation that I can use to solve for b. You can multiply the 9 and the 2 together, which gives us 18, and then subtract your 18 to both sides, and then you'll get b is equal to 5. So the y-intercept, or the starting value, the number of children they had in the beginning was 5 for daycare B. So if we had to write an equation to represent daycare B, we would say y equals 9x plus 5, where 9 is the number of children they're increasing by per week, and 5 is the number of children that they started with. So again, it's going to be daycare B, because they started with 5. All right, just want to double check my, yep, okay. All right, so hopefully that made sense. There's a lot of math involved in that one. Problem C. The graphs below show the distance of 2 runners over several minutes. Runner A is traveling at 500 feet per minute. Which equation below is the best choice for describing the distance covered by runner B after x minutes? Okay, so the graphs below here show the distance of 2 runners over several minutes. Okay, so, and then they tell us runner A is traveling at 500 feet per minute. which is nice, but they want to know which equation below is the best choice for describing the distance covered by runner B after X minutes. So this kind of like is one of those problems where they, I think, give you a little bit extra information. They're telling you about runner A, but they really want to know which equation describes runner B. So I'm not sure if we're going to necessarily need that information about A, but let's see. All right, so we've got, I know this is a little bit blurry, but distance in feet is what we have here. And then we have your minutes here. Oh, I guess I know why we have to have A, because basically it's whether or not you understand which slope is greater. So if the slope for this line for runner A is 500 feet per minute, or the rate of change, would the slope for runner B be greater than or less than the slope for runner A? So that is basically why you need to know about runner A. So because the slope for runner B, or the line for runner B, is steeper or increasing more rapidly than the line is for runner A, your slope should be greater. So the runner A, like we said earlier, is traveling 50 feet per minute, so, or 500 feet per minute. So that is the slope. Well, if you compare the slope for runner A with the slopes of these equations, the only equation that has a slope that's bigger than 500 is option C. So it would have to be the 650x, because that's the only one that has a steeper slope. It's not going to be the same. It's not going to be less than. Your slope has to be greater than the slope for runner A. All right, so that's that one. 13. Maria rode her bike home from school. Okay, so she's starting at school, and she rode her bike home from school. So she's going home, she's starting at school. The graph below shows Maria's distance from school over time. So the graph is showing Maria's distance from school. So that's an important piece of the information, and it's over time. So these x values, or along the horizontal axis, represents time in minutes, and this is the distance from school. And they want us to describe Maria's bike ride using the graph that's here with respect to the time and distance. Be sure to include any changes in speed during the bike ride. Okay, so let's think about what this point represents. This point represents 0 minutes and 0 miles from school. So then, and then as we go up the line, this point here represents that after 30 minutes, she is now 1 mile from school. So what's happening? Well, she's traveling at basically, she's traveling away from school. So in 30 minutes, she's traveling 1 mile every 30 minutes. So Maria leaves school and is 1 mile away after 30 minutes. And again, there's not one exact answer to this problem, but you want to definitely explain, show the points that you understand, what's going on, and explain enough so that whoever is grading the problem believes that you fully understand what's happening in this graph. Okay, well, at 40 minutes, if we look at this point, at 40 minutes, she is still 1 mile away from home. So if the distance is not changing, or from school, sorry, the distance from school. So if the distance from school is not changing, then basically she's stopped. So how long did she stop? Well, from 30 to 40, that's 10 minutes. So Maria stopped for 10 minutes. Okay, and so that describes that segment. And then from here to here, after 50 minutes, 1.5 miles from home, or from school. I keep saying from home. So after 50 minutes, she's 1.5 miles from school. And since the line ends there, the graph ends there, I'm guessing that she probably made it home by then, because it's telling us that the graph below shows Maria's distance from school over time, and she rode her bike home from school. So I'm guessing that after 1.5 miles, after 50 minutes, now she's home. But anyway, we have to kind of put this into that segment into the section here. So so Maria continues, or starts riding her bike again. And I'm not sure if I should say she gets home, because I can't assume that. Is 1.5 miles from school after 50 minutes. Okay, so what is this showing? Again, it shows that we understand that she's traveling, she's riding her bike, she gets 1 mile away after 30 minutes, she stops for 10 minutes, and then she starts riding her bike again, and she's now 1.5 miles away from school after 50 minutes. So we could maybe guess that she was at home, because it says Maria's bike ride home, so we could probably say that she made it home after 50 minutes, and home was 1.5 miles away. Something to that effect. All right, moving on. Okay, so this one's this lesson, this unit, the linear equations and inequalities and functions are worth, I believe, 35% of the ISTEP is going to come from this lesson. So that's why, if you notice, there's a lot of problems with this lesson, and it's because a lot of the test is going to be coming from this lesson. All right, Joe ran from his home to school at a constant speed. So that constant speed is important. That basically is going to tell you that you're going to have a nice straight line. It's not, he's not, increasing rapidly and then, slowly. He's increasing at a constant speed. So the rate of change is going to be consistent. He took a short break and then ran back home, but at a slower, non-constant speed. So non-constant speed means he could speed up, slow down, and again, we're going to be putting that in our graph. So Joe ran along a straight path to and from school. So even though he's running a straight path, that just means that the distance from home is going to be the same going there and back. Sketch a graph to represent Joe's distance from his home. So again, it's from his home over time, and then identify the independent and dependent variables. So your independent variable is the one that's on the horizontal axis. That's going to be time. And the dependent variable is on your vertical axis, which is the distance from home. If you were looking at an equation or a function, the independent variable is the one that's being plugged into the function or the input. The dependent variable is the output value. All right, so Joe ran from his home to school at a constant speed. All right, so he's at time 0, he's at home, but he's running to school, so his distance from home is going to increase, but it's increasing at a constant speed. So it doesn't really matter how steep your line is, as long as it's a straight line and and there's no curves in it. Then it tells us he took a short break. So the distance from home, if he's taking a break, is going to stay the same. But it's a short break, so make it short. Then he ran back home. So he's going to go back home, but at a slower, non-constant speed. So whatever steepness you made the line going from home to the break, you need to make this one less steep because he's going slower, but at a non-constant speed, so it's going to kind of have some curves in it. So maybe like this, and then like this, you know, so it's not real constant. So there's going to be maybe a curve in there. Maybe he speeds up here and then slows down and speeds up again. So there we have it. There's our graph. He's going away at a constant speed, takes a small break, and then returns back home at a slower but non-constant speed. All right. All right, ignore that. Moving on, now we're solving a couple equations here. So the first one here is a regular equation. The second one is an inequality. So we're going to solve these. They're multi-step, which so there's a couple ways you could do this problem. I'm just looking at it. You could distribute the 1/5 to both sides of the equation, but personally I think that multiplying by 5 on both sides would be a better option. So why might that be? Well, what's going to happen since you're multiplying this p minus 14, the p minus 14 and this 1/5 together? This is basically one. Think of this as one term because it's being multiplied together. So when you multiply this 5 times the 1/5, that will become 1, basically, times p minus 14. And that will get rid of the fraction, which everybody doesn't, since nobody really likes fractions anyway. And then when we distribute the 5, we'll get 50 plus 5p over there. Now if you multiply the 1 and distribute the 1 in, it's really not going to change anything. You'll have 1 minus 14 equals 50 plus 5p. So now we have simplified the left side, we've simplified the right side, we've gotten rid of our denominators. So now we have to start moving variables from one side of the equation to the other and constants. I like to personally get rid of the variable on the right and move it to the left, and then get rid of the constant that's on the left and move it to the right. With inequalities, you almost have to do it that way, but with equations, you could go either way, but again, I like to be consistent. And then since I am basically out of room here, I'm going to continue this up here, and then I'm going to do problem B up here above problem A. All right, so I'm going to rewrite this. P minus 14 equals 50 plus 5p. So I am going to eliminate the 5p, or subtract it from the right side, but you have to do whatever you do to the right, you have to do to the left. But I'm also going to eliminate the negative 14 from the left by adding it, but again you have to add it to both sides, so that's going to cancel out this and that. So the 1 is your coefficient here. 1 minus 5 would be negative 4p, and then 50 plus 14 will be 64. So then when we divide by our negative 4, we'll get p equals a negative 16. And there's our solution. So again, you could have distributed the 1/5 into the equation and then moved the variables and the constants, and you should get the same answer. This is just the method that I chose. All right, moving on to problem B. So I've got all this space up here. So I am going to do problem B up here. 2.5m minus 7 times m minus 3 greater than or equal to 40. So I'm going to rewrite it up there. All right, so once again, you have to simplify each side of the equation. In this side, the left side, you've got a negative 7 that's being multiplied by m minus 3. So you have to simplify that first. You have to distribute before you combine like terms. So we distribute the negative with the 7. So negative 7 times m is negative 7m. Negative 7 times a negative 3 is a positive 21. And then we're going to bring down that 2.5m. Now on the right side, we just have one term, so we do not need to change it or simplify it. We're still working on the left side, so we've got like terms here between the 2.5m minus the 7m. So the positive 2.5 and the negative 7. When we combine those like terms, you add the coefficients, which will give us a negative 4.5m plus 21 is greater than or equal to 40. Now you need to add or subtract. You got to eliminate the 21 from both sides of the equation. So I now have my new inequality. It's an inequality, not an equation. 40 minus 21 will be 19. And then my last step, I would divide by a negative 4.5. Now with inequalities, one of the major rules of inequalities is that when you divide both sides of the equation by something to solve it, or you divide both sides of the equation by a negative number to solve this inequality, the inequality sign flips from greater than to less than. So that's going to be really important. I'm almost positive there'll be something like that on the ISTEP, because that's a skill that they're definitely going to test, to whether or not you know that when you divide both sides by the negative, that the inequality sign flips. All right, so then the 19 divided by the negative 4.5 will be a negative something. Let me plug that in my calculator. And I get 4.2 repeating, which would basically be 4 2/9, because 0.2 repeating is equal to 2/9. All right, so there is our answer for problem B. Okay. Part C. At a ski resort, you can snow ski for $35 per hour plus a $15 fee for equipment rental. So the $35 per hour. So whenever you see a rate like that, it's probably representing the slope in this linear equation. Plus a fee of $15 for equipment rental. So that's a one-time fee, which means that's probably going to be your Y-intercept. Oh, well, I guess you're writing an equation for this one. They're telling you your bill. Your bill came to a total of $137.50. So how many hours did you snow ski? So they're trying to figure out how many hours you're snow skiing. Write an equation and explain how you found the solution. Be sure to justify each step. So this is something that they like to put on the ISTEP, where you have to justify each step. So to write your equation, you first of all want to have a variable that represents what it is that you're trying to find. So if you're trying to find how many hours you did you snow ski, make your variable something like h, which equals the number of hours snow skiing. I think that's how you spell skiing. All right, so h is the number of hours snow skiing. But you have to define your variables. They can't just be h equals hours. That's not good enough. You need to define what it is about the hours. Is it the number of hours? Is it how many minutes are in the hour? What about the hours? So number of hours snow skiing. So now we're gonna take the information, $35 per hour. So 35 times the number of hours plus the $15 fee is going to equal the total bill, $137.50. Okay, so we wrote an equation, we defined our variable, explain how you found the solution. All right, so to solve it, and we want to justify our steps. So we're going to subtract 15 from both sides. So when I'm justifying my steps, this is basically the subtraction property of equality. I'm not sure if they're going to want to be that precise. But